Hello everyone, myself Palluri Sumanth. I am studying Bachelor of Technology in Computer Science and Engineering at Jawaharlal Nehru Technological University, College of Engineering, Autonomous, Anantapur. In this video, I would like to explain you about selection sort, algorithm for selection sort and its source code, and about the time complexity of the selection sort. I made this video as part of my data structures assignment. So without any delay, let's get into the video.
Okay, let's see about different types of sorting techniques. Bubble sort, selection sort, insertion sort, mid sort, quick sort. And now we discuss about selection sort.
Before entering into the topic of selection sort, let's see what do you mean by sorting. In general, sorting means nothing but arranging the given data either in increasing order or decreasing order. But in most of the cases, the sorted data is arranged or stored in ascending order. Okay, let's get into the topic of selection sort. Selection sort is one of the simple sorting techniques, and as I said before, in selection sort also the data which is sorted is stored in increasing order. In selection sort, first element of the array is treated or considered as the smallest element of the array, and it is compared with the remaining elements of the array. In that comparison, if any element is found to the smallest element than the first element, then both the elements are swapped. This process continues until the entire array gets sorted. Let's see how selection sort works or algorithm for selection sort. Consider the following array as an example. The following array contains 14 at index I equal to 0, 33 at index I equal to 1, 27 at index I equal to 2, 10 at index I equal to 3, 35 at index I equal to 4, 19 at index I equal to 5, 42 at index I equal to 6, 44 at index I equal to 7. And now we take 14, which is at first position, to be the smallest or minimum element among the remaining elements of the array. Now we compare 14 with the remaining elements of the array. In the comparison, we found 10, which is at index I equal to 3, to be smaller than 14. So we replace 14 with 10. After one iteration, 10, which happens to be the minimum value in the list, appears in the first position of the sorted list, and after one iteration we get the array like as shown below. For sorting remaining elements of the array, we continue or repeat the same procedure as we followed above. Now we take 33, which is at index I equal to 1, to be the smallest or minimum among the list of elements present on the left side of 33, and now we have to compare 33 with the remaining elements which are present on the left side of it. Now we no need to compare 33 with 10 because it already sorted. In the comparison with the remaining elements, we found that 27, 10, 19 are minimum elements, but as we know, in the entire list 14 is the second lowest value. So now we have to swap 33 with 14. After swapping, we get 14 in the second position. After comparing 33 with the remaining elements of the array which are present on the right side of it, we found 14 to be minimum than 33. Now we swap both 33 and 14. We get 14 at I equal to 1st position. Now we take 27 to be smallest or minimum than the remaining elements present on the right side of it. So now we have to compare 27 with the remaining elements of the array which are present on the right side of it. No need to touch the left side part of it because the left side part of it is already get sorted. So in the comparison we found 19 to be smaller or minimum element than 27. So now we have to swap 27 and 19. Follow the same procedure for sorting the remaining elements of the array. In the earlier section we discussed sorting up to I equal to second position. For the remaining positions we discuss now. Now we take 33 to be minimum element or smallest element among the list of elements present on the right side of it and compare with them. In the comparison we found 27 to be smaller than 33. So we need to swap 33 and 27. After getting swap, 27 gets its position at I equal to 3. Now we have to take 35 to be smaller element than the list of elements present on the right side of it and compare with them. In the comparison we found 33 is the smaller or minimum than 35. So we need to swap 35 and 33. After getting swap, 33 gets its position at I equal to 4. Now we have to take 35 to be minimum or smallest elements among the list of elements present on the right side of it, and it is compared with 42 and 44. As we know, 35 is smaller than 42 and 44, so it stays at its own position at I equal to 5. Now we have to take 42 to be minimum and it is compared with 44. 42 is smaller, so it stays at its own position. 44 already gets swapped, so it's in its own position. The resultant array.
Let's see about one more important topic, time complexity.
Okay, let's get into the topic of time complexity. What is time complexity? Time complexity of an algorithm signifies the total time required by the program to run till its completion. And time complexity of algorithms is most commonly expressed by using the big O notation, and this notation is also called Landau's symbol, and it is an asymptotic notation to represent the time complexity. Time complexity for any algorithm is most commonly estimated by counting the number of elementary steps performed by the algorithm to finish its execution. Since the algorithm performance may vary for different types of input data, hence for an algorithm we usually use the worst case time complexity of an algorithm because that is the maximum time taken for any input data.
Big OH denotes fewer than or the same years of that of expressions but greater than iteration. Big omega denotes more than or the same as that of expressions but greater than iteration. Big theta denotes the same as that of expressions but greater than iteration. Little OH denotes fewer than or the same as that of expression but greater than iteration. Little omega denotes more than or the same as that of expressions but greater than iteration. Time complexity for selection sort. In computer science, selection sort is an in-place comparison sorting algorithm. It has an order of n square time complexity, which makes it inefficient on larger lists and generally performs worse than similar insertion sort. Selection sort is noted for its simplicity and has performance advantages over more complicated algorithms in certain situations, particularly where auxiliary memory is limited. Let's see some of the time complexity cases for an array when it is sorted by using selection sort. Worst case performance, order of n square comparisons, order of n swaps. Best case performance, order of n square comparisons, order of 1 swaps. Average performance, order of n square comparisons, order of n swaps. Worst case space complexity, order of 1.